Hey everybody, welcome back. So the purpose of this video is to provide students that are taking perhaps a pre-calculus course or a trig course with more examples of verifying trig identities. And for all the problems, I haven't gone through them yet, so I wanted to sort of take you through the process of solving them from scratch as I would, and try to clue you into some of the tricks of the trade. So first of all, we want to recall some classic identities from trig. And so these are essentially all the reciprocal identities. They're really handy. They allow us to transform one thing into another, and we'll use them all over the place. In general, it's pretty handy to know the even and odd function properties. And so remember that cosine and its reciprocal secant, those are even functions, right? They have y-axis symmetry. And so this is true for all x's in their domain, right? And for sine, cosecant, tangent, and cotangent, these are all odd functions. They have origin symmetry or 180-degree rotational symmetry. So these are all nice to know. And so today in particular, we're going to use the classic Pythagorean identities quite a bit. So the first one is for all thetas, sine squared of theta plus cosine squared of theta is 1. Keep in mind the idea here is that theta is the same, right? This is for some fixed theta. And from this, algebraically, we get these. And these are handy because I can transform a statement about sine squared into cosines, right? Same deal, I can take a statement about cosine squared and transform it into a statement involving sines. So very, very, very handy. And so we get the next classic Pythagorean identity. Tangent squared of theta plus 1 equals secant squared of theta for all theta for which this is defined. And from this algebraically, we get these. Again, very handy because you can take a statement involving tangent squares and turn it into this. And depending on the context, that can be really, really helpful. Same idea here. This difference is 1. So maybe if I factor something, sometimes if you're factoring the difference of squares, like if I've got a secant to the 4th minus a tangent to the 4th, this thing would pop out when you factor, and realizing that that's 1 is very nice. Okay, so for the next classic Pythagorean identity, we have the following. So we have 1 plus cotangent squared of theta equals cosecant squared of theta. And from this algebraically, we get these. Okay, so I can transform a cotangent squared statement into a cosecant statement. And I realize that this difference is 1. Again, this is just by a little algebra here. Okay, so we're about to go into solving a bunch of trig identity problems. And you want to be on the lookout for maybe sometimes we use common denominators, reciprocal identities, we factor, Pythagorean identities. All of these things can be super, super helpful. Okay, so without any more delay, let's go ahead to the solving. Let's see what the first problem is. Okay, so all I've done is I've written these down. I have not solved these ahead of time. So let's see what we can do here. Now, typically when I solve these, well, not solve, but I verify the trig identity, I try to work with the harder side or the side that's seemingly more complicated because it gives me more to work with or more to collapse down. You don't have to if you're super, super creative. You can work with the less complicated side and, be clever algebraically and try and build a bridge to the other side. But let's see what happens if perhaps we work with the left side and we try to build a bridge to the right side. So when I verify identities, I'm going to choose one of the two sides, work with that, and try and show that it's equal to the other. I'm not going to work with both sides. I'm going to do this sort of proof by chain of equalities. Okay, so let's see what working with the left side gives us. So tangent squared of theta times cosine squared of theta. Let's see here. Well, I know that tangent squared is equal to sine squared of theta. over cosine squared of theta. So maybe I'll rewrite that. I still have this cosine squared of theta. Okay, so it seems like the cosines are going to cancel. Initially, I might be concerned because I'm trying to build a bridge here and I'm getting rid of my cosines. But in the spirit of adventure, let's see what happens. So those will cancel. I've got a sine squared, and then I think to myself, okay, is there any sort of connection between sine squared and cosine squared? And if you remember the Pythagorean identity, there is. Because we said earlier that sine squared of theta is exactly 1 minus cosine squared of theta. Okay. So we verify that. Let's see what's up next. Okay, so I've got 1 plus tangent of theta over sine of theta plus cosine of theta, and I want to verify that that's equal to secant of theta. Okay. When we say a statement like this, we mean for all theta for which this is defined in corresponding domains, right? So I'm not writing that each time explicitly, but it's sort of understood. Okay, so let's work with the more complicated side because it just gives us more to work with and see if we can show that this is equal to this. Okay, so the first thing I notice is that I've got sine and cosine, something that's not in terms of sine and cosine. So one thing you might consider is to just write everything in terms of sines and cosines because sometimes that's pretty fruitful. Let's see if that's helpful. And again, I don't know where this is leading, so you need to have sort of a spirit or sense of adventure. Okay, so let's see what we have here. So tangent of theta is sine of theta over cosine of theta over, let's see here, we've got sine of theta plus cosine of theta. Okay, let's see what we can do next. So there's some options here. So I'm thinking about maybe, I mean, this thing's a fraction. This is not. Common denominators might be helpful. Let's see what happens. So I could take this and I could think about 1 as cosine over cosine, and that might be helpful. So what's sort of the moral or the upshot here is maybe if one thing or one term is a fraction and the other isn't, maybe considering common denominators is perhaps useful. So yeah, let's try that. So 1 is cosine of theta over cosine of theta. Okay, so that seems nice. And if you're sort of bothered by this right here, remember that when you have a complex fraction, dividing by a fraction is the same as multiplying by the reciprocal. And so the reciprocal of this is 1 over sine of theta plus cosine of theta. That seems nice. Okay, so yeah, this is promising because I've got common denominators. Look what's happening here. Okay, so I'm really liking this. We have this common denominator of cosine, and I see some cancellation. So I'm really hopeful. So these will cancel, right? Any object over itself is just 1. So I get 1 over cosine. So yeah, 1 over cosine of theta. But that's one of our reciprocal identities, right? So 1 over cosine of theta is exactly secant of theta. So that's nice. We were able to verify our trig identity. Okay, so that's another one. I'm happy about that. Okay, let's dive right into the next. Okay, so this looks like a lot's going on here. And so again, I want to think about my options. The first thing I notice is that everything is in terms of cosecants. So my mind is saying maybe you want to consider keeping this in terms of cosecants. It might be helpful. Another thing my mind is thinking is maybe factoring would be helpful. I mean, this looks like a trinomial, right? This reminds me a lot of perhaps something like this. So when I see something like this, I think of like x squared plus 2x minus 3. Just x is cosecant of theta, right? And I know one of the options I would have with a trinomial like this would be to perhaps factor it. And depending on the context, that could be useful. And so I'm thinking, I don't know, x plus 3, x minus 1. Maybe we could apply that thinking here. And then downstairs in the denominator, maybe I could factor that as well. So another option when dealing with trig identities is factoring. Okay, let's see what's up here. So I chose to work with the left because it's more complicated and it gives me more to work with. Okay, so yeah, let's factor the numerator just like we would a trinomial. So this is going to be, it looks like cosecant of theta times cosecant of theta. And then let's see here. So we want the signs to be different. So how about 3 and 1? And of course you could verify by multiplying that you get this. Okay, so that seems pretty nice. And then, so I think we said earlier that we could think about this as the difference of perfect squares. So let's factor that as the difference of squares. So that would be cosecant of theta minus 1, cosecant of theta plus 1. And that's really nice. We can cancel this factor. And that wasn't so bad. It just looked intimidating, but with a little bit of care and thought, we got there. So I'm happy about that as well. Okay, so we're on a roll. This is good. Okay, so let's keep going. Okay, so when I see a statement like this, the first thing my mind goes to is I want to transition from a radical to an absolute value, and I want to recall, maybe I'll put this on the side here. So I want to recall this because I have a feeling it'll be useful, that the square root of x squared is equal to the absolute value of x. Okay? Okay, so that's sort of in my mind. So maybe I should work with this more complicated side and see if we can get it to equal this. Okay, so lots going on here. I want to transition to a statement about sines. Maybe I should turn everything into sines and cosines. Let's see if that's helpful. Remember, go in with a sense of adventure. If you take a path that doesn't lead anywhere nice, just restart the problem. At least you tried something. And there's learning in those sort of failed paths. So yeah, it's worth it. So here I've got sine of theta still. Now tangent we know is sine of theta over cosine of theta. And then secant, that's 1 over cosine. That's still inside of the radical. Maybe I'll write it like that just to suggest that's all in the radical. Okay, So this seems pretty good because we've got this complex fraction, and maybe we could multiply by the reciprocal of this, and the cosines will cancel. So I've got this sine times sine is sine squared of theta, of course. That's over cosine of theta. And then we're multiplying by the reciprocal of this. Okay, so that seems really nice. The cosines will cancel. I've got the square root of sine squared of theta. And by our classic property, that's exactly the absolute value of sine of theta. Okay, so I'm happy about that. Also, this is a great problem because it's another opportunity to reinforce this idea. And when it comes to calculus, I apply this idea in Calc 2 all the time. Okay, let's see what's up next. Okay, so I want to transition into a statement about the sum of fractions into a statement about secants. So let's work with the more complicated side and see if we can reduce it down to a statement about secants. Let's see here. So when it comes to fractions and adding or subtracting fractions, you probably want to at least consider getting common denominators. It might not be your only option, but it's certainly an option to consider. So a nice common denominator, it seems like, might be the product of these two. So maybe I'll multiply this by 1 minus sine of theta over 1 minus sine of theta to give me common denominators. So maybe I'll write that. So I want to multiply by 1 minus sine of theta over itself. Sometimes we call this a useful form of 1 or a well-chosen form of 1. And again, the point of this is to give us common denominators when we add fractions. And then over here, so let's write that down. We're going to multiply this by 1 plus sine of theta over itself. Again, with the goal of getting common denominators, but in a legal way. Okay, so I'm feeling pretty good about this because it looks like we have nice common denominators. Okay, so we'll have common denominator of 1 minus sine of theta times 1 plus sine of theta. Sometimes in math we call these conjugates, right, where the left and the right are the same, but you have opposite middle signs. And let's see what's going on upstairs. So I'm going to have cosine of theta times 1, so I'm using the good old distributive property here. This will be minus sine of theta times the cosine of theta. And then plus, right? We'll also distribute this. So we've got cosine of theta plus cosine of theta times sine of theta. And just for a moment, it might seem like we've got a bit of a mess, but we actually don't, because these are the same, but opposite sign, right? So these will cancel. These are additive inverses. And so those are gone. Remember, it doesn't matter which order I write them in. Multiplication is commutative or order switching. That means that this is actually identically the same as this. So yeah, these will cancel. No problem there. And then I've got these like terms here, right? Cosine plus cosine means I've got two cosines. That seems promising because I'm at least recovering this 2. So maybe I'm headed in a good direction. And we'll multiply these. So remember, when you multiply these real conjugates, like you have here, you're going to end up with a squared minus b squared. And you can verify that by multiplying out. But that's really nice because that's one of our Pythagorean identities. Remember that? 1 minus sine squared of theta is exactly cosine squared of theta. That's really useful. So by our Pythagorean identity, we get the following. And see, we're doing this live here, folks. I'm going to need some more paper. Okay, so that seems good. Let's overlap it like this. We can cancel out one factor of cosine from the top and the bottom. That gives me 2 cosine of theta. But that's one of our reciprocal identities, right? So I know that by our reciprocal identity for secant, a downstairs cosine is an upstairs secant. And so we verified it. So I'm happy about that one. Okay, so let's venture on. What's next up? Okay, so we have a statement involving logarithms, right? So we've got the natural log. Remember what that means? It's a logarithm in base e, or Euler's number base e. So we've got the natural log of the absolute value of cosecant of theta plus cotangent of theta plus the natural log of the absolute value of cosecant of theta minus cotangent of theta. And we want to show that this is equal to 0. Okay. I think it might be handy to think about properties of logarithms. So this would be a good time to recall something. So let's recall, in particular because I see a plus, right? So remember that the natural log of a times b is equal to the natural log of a plus the natural log of b. That means I can go from a statement that has the natural log of a product and turn it into a sum of natural logs, or I can take a sum of natural logs and rewrite it as the single natural log of a product. So I go from here to here, or from here to here. Let's go from here to here. That seems useful. Also notice that knowing these properties is nice because at first you might look at this and go, yikes, that's kind of scary. But it's not so bad if you know these. Okay, so let's see what we have here. So of course, we're going to work with the left side and show it's equal to the right. Okay, let's work down this way. So by this property, we have a single natural log of the product of the inside. Okay, so a sum can be rewritten like this. So if this is A and this is B, then I want to write their product, A times B. Well, that's nice because, again, we have the product of conjugates, right? You've got like x plus y times x minus y. That should be x squared minus y squared, right, when I take the product of conjugates. So that'll be cosecant squared of theta minus cotangent squared of theta. Now let's see here. Do we know any properties that relate cosecant squared and cotangent squared? Let's recall this. Because we have a very, very nice Pythagorean identity that says 1 plus cotangent squared of theta is equal to the cosecant squared of theta. Right, that was the third Pythagorean identity that we mentioned earlier. And if I subtract this from both sides, I can see that their difference is exactly 1. And that seems very nice. So this difference is exactly 1. Well, 1's positive, so I don't need, absolute values here. It's not wrong to keep them, but I certainly don't need them. And of course, we know the natural log of 1 is 0. And that's because e to the 0 is 1. So this one was nice because you had to know your natural log properties. You had to realize that you're multiplying conjugates, and so you multiply them out and get the difference of squares. And then you had to realize that, oh, that's a Pythagorean identity. And then lastly, that the natural log of 1 is 0. So yeah, that's a cool one. Ready for another? Let's do it. Okay. So I claim that the fourth power seems, in a sense, more complicated than these squares. So let's work with the left side. I don't think this one's going to be so bad. Because the first thing I notice is that we have the difference of squares, right? And so we can factor the difference of squares. Let's go ahead and factor the difference of squares. So that should be cosine squared of theta plus sine squared of theta. That's an old friend. Times cosine squared of theta minus sine squared of theta. And that seems nice. So there's another classic Pythagorean identity showing up. This is exactly 1. And so this one was practically instant. Well, that's a nice breather. Okay. All right. Not bad. Let's see what's up next. Okay, this one looks a little bit more involved. Let's see what's going on here. Okay, so we've got the cosecant of theta plus the cotangent of theta times 1 minus cosine of theta, and we want to show that this product is equal to sine of theta. Okay, let's see here. Now I could turn everything into sines and cosines, but maybe I'll multiply this out first and see if that goes anywhere fruitful. So we have some options here. And again, I might be taking a path that complicates things. I'm not sure. I'm just diving in with a sort of sense of adventure. Okay, so let's multiply here. So that's going to be cosecant of theta minus cosecant of theta times cosine, right? So just distributing. And then I distribute here, so that's going to be a cotangent of theta, and this will be a cotangent times cosine. Let's see what's going on here. So cotangent times cosine. Okay, so maybe, just maybe, we'll turn everything into sines and cosines now. So cosecant, that's a reciprocal identity, right? That's 1 over sine of theta. So cosecant of theta. If I ever say the trig function without the angle, just assume that I mean the angle in context. Okay. So here this is going to be 1 over sine of theta times cosine of theta. Oh, that seems nice. That seems nice. Plus cotangent, which is cosine of theta over sine of theta. And then here, what's going on over here? Let's see. Cotangent of theta. That's cosine of theta over sine of theta. And this is times the cosine of theta. So I hope that's clear. So let's just double check. So that seems fine. This is this. This is this. That's good. Cotangent is exactly this. And then cotangent is this times sine. So that's good. Check this out. This is pretty nice. because these are the same thing but opposite signs, so they're additive inverses, so they're going to cancel. So let's see what we're left with. We've got 1 over sine of theta, so that seems good. Again, these canceled, and then I've got this minus cosine squared, right? Cosine times cosine is cosine squared. Theta over sine of theta. That seems pretty good because we have common denominators, and I hope at this point you're noticing something else as well. Because here you have a classic Pythagorean identity, right? 1 minus cosine squared of theta. That's exactly sine squared of theta. Okay, so that Pythagorean identity coming to the rescue once more. And so at this point, we can cancel a factor of sine from the numerator and the denominator, and we're left with exactly sine of theta. So that's nice. And so again, I really want to stress that sometimes, you might go into a problem and you'd say, I have no clue the exact steps I should perfectly take to go from here to here. That's fine. Just go for it. Try something, right? Just try all sorts of avenues, because again, that's how you're going to poke around and build your intuition for things that work and don't work. So that sense of adventure is absolutely crucial. It's crucial. It's more fun too. Okay. Let's see what's up next. Okay, this sort of seems similar to one we saw before, so I'm not terribly worried about this. Just like before, let's work with a more complicated side and try and turn it into this side. So I'm going to work with the right side. And I hope you're noticing the difference of squares. So I think right off the bat, it might be a good idea to factor the difference of squares. So this is secant squared of theta plus tangent squared of theta. That's promising. And this is times its conjugate, right? Secant squared of theta minus tangent squared of theta. But we want to recall something. So recall that tangent squared of theta plus 1 is equal to secant squared of theta. That's our second classic Pythagorean identity that we talked about earlier. And you'll notice if you subtract tangent squared of theta from both sides, you get that 1 is exactly equal to this difference. That's helpful. So that's 1. So yeah, this one was practically instant. What's the little moral or upshot from this problem? Consider factoring and be on the lookout for Pythagorean identities. Okay, on to the next. Here we go. And so this is exactly what I mean when I say you want to sort of go in with a sense of adventure, right? Because I have no clue where we're going to head with this. So let's plunge in. Let's have some fun. Okay, so we're going to work with the left side. Let's try common denominators. Let's see what happens. That might be useful. And so I'm going to multiply this fraction by essentially this over itself. So yeah, let's take the left fraction and multiply it by cosecant of theta minus 1 over itself. So that's cosecant of theta minus 1 over cosecant of theta minus 1. And again, that will be multiplied by this. Again, the reason why I'm doing this is for common denominators. That might lead somewhere nice. Okay, and then with the same sort of thinking, let's take this right fraction and multiply it by this over itself, right? So we'll take this and we'll multiply it by cosecant of theta plus 1 over cosecant of theta plus 1. Let's see what that looks like. Okay, so here's the right fraction. And we're multiplying it by cosecant of theta plus 1 over itself. Okay, so I have common denominators. I'm pretty happy about that. So this is my single denominator. Right, they match, so that's good. Let's see what's up in the numerator. So this times 1 should be exactly a copy of that, plus this times 1. So it looks like the ones will cancel, and these are like terms, so one of these plus another one of these is 2 of these. That's nice because that at least gives me the 2. And then I noticed downstairs I've got, again, the product of conjugates. So that's just like having x minus y times x plus y. We know that'll be x squared minus y squared. But in context, that's cosecant squared of theta minus 1. Okay, but this reminds us of a Pythagorean identity from earlier, right? So let's look at this. So from earlier, so going way, way back, I think we had something like this, right? So this is exactly equal to this. So this is this. So let's replace that. So Pythagorean identity. So this is 2 cosecant of theta over cotangent of theta. And maybe we'll rewrite this in terms of sines and cosines. Good, need another piece of paper. Again, we're doing this live. So let's see. Okay, so yeah, we're going to rewrite this in terms of sines and cosines and just, we'll see what happens. We'll see what happens. So I've got 2 over sine of theta. That's exactly this. And then downstairs, I've got this cotangent, but cotangent is cosine of theta over sine of theta. By the way, did you notice something? Did someone forget a square? I think that should be squared, of course. Okay, there we go. Yeah, don't forget your square like I did. That Pythagorean identity says that that's equal to cotangent squared of theta. Okay, so that's fixed. We're good. So now that we have that, we want to take this and just rewrite it. Let's multiply by the reciprocal. So that's going to be sine squared of theta over cosine squared of theta. Let's clean that up. Let's cancel out a factor of sine. So that's going to give me 2 sine of theta over, looks like cosine squared. But I think we have this if we use our reciprocal identity for secant or cosine. So remember, so we're trying to land here, right? We want to land back here. And so remember that downstairs, so I'll speak informally, downstairs cosine is upstairs secant. So that gives me 2 times secant squared of theta times sine of theta. So that was quite a journey. Okay, so very happy about that one. What's the moral for that one? Don't forget your square. Don't forget your square. Okay, let's see what's up next. Okay, so yeah. Not sure where to start. Let's start with the right side, maybe. Maybe that's more complicated. We can turn that to the left. Like I always say, you have to have a sense of adventure. So let's sort of plunge in and see what happens. So let's see what happens here. So we're trying to turn this into a statement involving tangents, right? A statement involving tangents. So maybe we could use a Pythagorean identity to do that. Right, so I think from earlier we had this. And this might be useful here, right? So we can turn statements involving secants into statements involving tangents. Let's see if that's helpful. That might be helpful here. So exactly this idea. So this will be 2 times. Now secant squared is exactly this. Minus secant to the 4th. Well, if I just square both sides, that's going to give me secant to the 4th of theta, right? So tangent squared of theta plus 1 by itself would be secant squared. But I want to square that, because that'll be secant squared squared, or secant to the 4th of theta. Okay. Yeah, let's do some algebra. What the heck? Let's distribute, and then let's square and see if anything nice comes out. So this is going to give us 2 tangent squared of theta plus 2 minus, so I'm going to square this. So that's tangent to the 4th of theta plus 2 tangent squared of theta plus 1. Okay, so double check. That seems good. That seems good. That seems good. Maybe we'll distribute. See what I mean by sense of adventure? Okay, let's see what happens when we distribute. Fingers crossed. So this is tangent to the 4th of theta, and it's minus, so that seems promising. Minus 2 tangent squared of theta minus 1. And so these will cancel, right? They're additive inverses, so that seems pretty nice. Let's see here. 2 minus 1 is 1, and I've got this left over. Okay. So that one was more recognition of the Pythagorean identity, and then just carrying through with a bit of multiplication, squaring that out and distributing the 2. Okay, so yeah, try something. Sometimes they're better than they seem. Okay, let's see what's going on here. Okay, let's work with this more complicated side. We'll try to turn this into this. And I'm thinking, I'm trying to land here, right? A statement about sines and cosines. So maybe I'll turn everything into sines and cosines. That might be helpful. So here I've got sine of theta. This is over 1 minus, so remember our definition of cotangent. That's the cosine of theta over the sine of theta plus cosine of theta over, now remember tangent. Tangent is equal to the sine of theta over the cosine of theta, so that seems okay. And let's see here. So I'm not super thrilled about these complex fractions, these fractions within fractions. But let's look downstairs. Because I think if we multiplied this by cosine, can you imagine them canceling? Let's take this and multiply it by cosine of theta over cosine of theta with the hopes that the cosine of thetas would cancel out here and we get rid of the complex fraction. Let's see if that's helpful. And then over here, I'm not too thrilled with the sine of theta in the denominator of a complex fraction. So let's multiply the top and the bottom by sine of theta with hopes that those would cancel out. Let's see what that looks like. So I still have this. Again, what's motivating this is, again, I'm not thrilled about this sine of theta there. So yeah, let's multiply the top and the bottom by sine of theta over sine of theta. And so you can imagine as you distribute, those would cancel there, and that's going to be nice. That gets rid of my complex fraction, right? My fraction within a fraction. Same thinking here. Let's multiply by cosine over itself. I'm not thrilled with this, and that'll help get rid of that. Okay, so upstairs we have, looks like sine squared of theta. Let's see what's happening downstairs. So again, I've got to distribute this to both terms here. So sine of theta times 1 is sine of theta. And then sine of theta times this, we'll have the sines cancel, and I'll just have the cosine. Over here, pretty similar. I've got cosine of theta times cosine of theta. That's cosine squared of theta. Over again, I'm going to distribute. So this times 1 is cosine of theta. And then here, the cosines will cancel out. That was actually the entire point, right, of multiplying by this. And so we almost have common denominators. Not quite right now, right? But I think if we're smart, if we factor out a -1 here, or still tons to go. Okay, if we factor out a -1 there, so yeah, let's factor out a -1 from the denominator. Then I can rewrite that. Let's do that. So maybe I'll move this up. And so I've got sine squared of theta over sine of theta minus cosine of theta. So this would be minus, because I'm factoring out a -1 here. And if I factor out a -1, then that means the sine will be positive and the cosine will be negative. That gives me common denominators, so that seems pretty nice. And again, let's look back where we're trying to land here. Where do we want to land? If we do this correctly, we land here. So yeah, let's see here. So common denominators, I've got sine squared of theta minus cosine squared of theta. That's not 1, so it's tempting, but it's not, so please be careful. Downstairs, I've got sine of theta minus cosine of theta. And we're almost there, but do you notice the difference of perfect squares? So yeah, let's factor this numerator, because this will factor, the numerator will factor into sine of theta minus cosine of theta times its conjugate. Okay, well, that seems nice because, well, we've landed where we need to land, right? We've verified the identity. Okay, what's next? Okay, so we want to show that this is equal to this. I don't know what side's more complicated in this case. Maybe the left side gives me more to work with? I don't know. Maybe the right side? Well, let's just pick one. Let's see here. Let's pick the left side. Let's see what happens. I see a path going from the right to the left. Let's just do the opposite. Let's see what happens. Again, we have to have a spirit of adventure here. Okay, so let's square this out. Let's see what happens. So that'll be the first term squared minus 2 times the product. Is everyone at home yelling at me? No, work with the right side, work with the right side. Let's have some fun. Let's have some fun. Okay, so let's see here. Well, I think we have a Pythagorean identity from before, because remember this? Oh, we don't. That's not minus. That's not minus. That's not minus root 66. Okay. Okay, let's turn things into sines and cosines then. Right? Let's do that. So that's 1 over sine squared of theta minus 2 times 1 over sine of theta, and then cotangent is cosine of theta over sine of theta. And then cotangent squared is cosine squared of theta over sine squared of theta. It looks like I have common denominators, right? That's sine squared, and that's sine squared. So it almost seems like it's for free, right? So for free, I get common denominator of sine squared. Okay, that seems nice. Let's see what's upstairs. I've got this 1 minus 2 cosine of theta plus cosine squared of theta. Okay. Well, the top sort of reminds me of a trinomial, like when you're trying to factor polynomials. So for example, I think we saw this idea earlier, but this does come up quite a bit. So for example, this numerator, this is sort of side work, kind of reminds me of this. And that's exactly the same as this, right? And if I wanted to factor that, that would be x minus 1 minus 1. And so that would be x minus 1 quantity squared. Maybe we could apply that same thinking here, and that might be useful. Let's try that. Okay, so here at this numerator, this will be, let's see here, cosine of theta minus 1 times cosine of theta minus 1. Again, you can check. This times this gives you the cosine squared. This plus this gives you the minus 2 cosine of theta, and this times this gives you the positive 1. So this factorization is good. Okay, I think we're close, because by our Pythagorean identity for sine squared, we can call this 1 minus cosine squared, right? That's a classic Pythagorean identity. But then this is the difference of squares, and we can go ahead and factor that. So that seems really nice. So this is 1 minus cosine of theta times 1 plus cosine of theta. Okay, so that seems pretty nice. Okay, and it looks like these, it might be tempting, I think, to cancel these, but they're sort of off by a factor of -1. So let's take one of these, perhaps this one. Let's factor out a -1 here. Grab a piece of paper. Like I said, we're doing this live. And so, yeah, let's factor out a -1 in particular from this. So that'll give me -1 times 1 minus cosine of theta. And then I've got cosine of theta minus 1. And you can see if I redistribute, there's the -1. And then there's the positive cosine, so it's perfectly fine. And then downstairs, we've got 1 minus cosine of theta times 1 plus cosine of theta. So that seems pretty good. So these will cancel, and then we can just distribute this negative over here. Right? And I think that's going to give us what we're looking for. So let's, again, look where we want to land. That's where we want to land. So yeah, let's take this and distribute over both terms here. That'll make the 1 positive and the cosine negative. And that's exactly what we're looking to do. So that seems good. Okay, what's up next? Okay, so yeah, let's work with the left side here and try and get this equal to the right side. Let's see here. I've got tangent of theta times the cosecant squared of theta minus tangent of theta. The first thing that hits my eye is this greatest common factor, right? I've got this greatest common factor of tangent of theta. Let's factor it out. Let's see if it leads anywhere. So here I've got tangent of theta times cosecant squared of theta minus 1. But remember, that's one of our Pythagorean identities, right? Cosecant squared of theta minus 1 is exactly cotangent of theta, or squared, right? So cosecant squared of theta minus 1 is the cotangent squared of theta. Okay, that actually seems pretty helpful because you need to realize that tangent and cotangent are reciprocals. And what happens when you multiply reciprocals? Well, you get 1, right? Just like multiplying 2/3 and 3/2, the result is 1. That's what happens when you multiply tangent and its reciprocal, cotangent. Let's split that into 2 copies of tangent. So yeah, these are reciprocals. So their product is 1. And so that gives me cotangent of theta. So that's not so bad. That one was okay. Okay, let's try the next. Okay, so yeah, sense of adventure, right? Sense of adventure here. Let's see what's going on. So let's work with the left side. And we'll try to get it to equal the right side here. So one thing we could do, we might try to get everything in terms of sines and cosines. So again, you might see a quicker avenue, and this is, you just have to plunge in and try something, right? So yeah, let's try something. So secant, that's 1 over cosine, right? So that's 1 over cosine of theta. That's over sine, but another way to say over sine is over sine over 1, right? Okay, so there's your secant, there's your sine. Got sine of theta, cosine theta here. I'm going to multiply by the flip or the reciprocal of this. And that's going to give me 1 over cosine of theta times sine of theta, right? So when I multiply by the reciprocal of this, I get this. Okay, so I've got 2 fractions. I'm looking to subtract them. Maybe I should think about common denominators. So maybe if I multiply this by sine over sine, I'm going to have the common denominators that I'm looking for. And let's see if that's helpful. So my numerator will be 1 minus sine squared of theta. That could be helpful. And my denominator will be this product of cosine and sine. Okay, well, this is a Pythagorean identity, right? 1 minus sine squared of theta, that's exactly cosine squared of theta. That's over cosine of theta times sine of theta. And you'll notice that looks like a factor of cosine will cancel. Let's move that up a bit. And so canceling out a factor of cosine gives me cosine of theta over sine of theta, but that's exactly the definition of cotangent. Okay, so we got it. Okay, let's see what else is up. All right, so let's work with this side and show that it's equal to this side. Just seems like I've got more to work with here. So I've got secant to the fourth of theta minus tangent to the fourth of theta plus secant squared of theta. Let's try distributing this negative, right? Let's multiply through by this -1. So that gives me secant to the fourth of theta minus tangent to the fourth of theta. That seems good because it's the difference of perfect squares. So that might be helpful. And so let's factor this, right? So I can factor this into the product of conjugates. So that's going to be secant squared of theta minus tangent squared of theta times secant squared of theta plus tangent squared of theta minus secant squared of theta. Okay, so that seems good. And hopefully you notice a Pythagorean identity because this difference is exactly 1. So that seems pretty good. So if that's 1, it looks like I'm left with this minus secant squared. So I've got secant squared of theta plus tangent squared of theta minus secant squared of theta. So these will cancel. I'm left with a tangent, and I have a feeling we have to creatively rewrite this. So tangent squared, rather. So what is tangent squared? So this is exactly sine squared of theta over cosine squared of theta. But I know that downstairs cosine is upstairs secant, right? Just by reciprocal properties. And this is exactly where we wanted to land. Well, that seemed pretty nice. Okay, what else do we have here? Okay, so for sure we should work with this side. We want to turn this into sine stuff. So cosecant of theta minus cosine of theta times cotangent of theta. Maybe we'll write that in terms of sines and cosines because we want to land at something involving sine. That might be helpful. Let's see what happens. So I've got 1 over sine of theta minus cosine of theta times, well, cotangent. We can rewrite cotangent as cosine of theta over sine of theta. But I don't think that's going to be so bad because it looks like we have common denominators. But you can put that over 1. So we will have common denominators of sine of theta. And then upstairs I'll have 1 minus cosine squared of theta, but that's a classic Pythagorean identity. So that's sine squared, right? 1 minus cosine squared of theta, sine squared of theta, over sine of theta, and 1 factor of sine will cancel from the numerator and the denominator. Okay. Notice sometimes you, as a student, you can sort of get in your own head and say, oh, yikes, that has cosecants and cotangents. Maybe it's more difficult than I'd like it to be, but no, it's fine. Just carefully use definitions and properties and watch it unravel. All right. Let's see what's going on here. Let's work with the left side and try and turn it into the right side. Let's see what happens. So we want to get to a statement about cosines. So let's rewrite everything in terms of sines and cosines. So tangent squared, this is sine squared of theta over cosine squared of theta. And then cotangent, this is cosine squared of theta over sine squared of theta. Lots of options here. I could multiply the top and the bottom by sine squared times cosine squared. That might be helpful. I could get common denominators. Let's do that maybe. So yeah, lots of options I'm trying to get at. Lots and lots of options. So this one, I can think about this as cosine squared of theta over itself. Downstairs, I can think about this as sine squared of theta over itself. Okay. Let's write these with their common denominators. So the numerator will be, looks like cosine squared of theta minus sine squared of theta over a single denominator, right, of cosine squared. And then downstairs in the denominator here, I'm going to have, looks like sine squared of theta minus cosine squared of theta over a common denominator of sine squared of theta. Okay, let's multiply by the reciprocal. See if anything nice happens. Again, when you're not sure of where to go, just have to plunge in and try something. Sometimes you take a longer path, sometimes it's shorter. Sometimes it doesn't lead anywhere, but you got to try something. Okay, so upstairs I've got cosine squared of theta minus sine squared of theta. This is over, looks like cosine squared of theta. And then multiplying by the reciprocal here, I've got sine squared of theta over, here I've got sine squared of theta minus cosine squared of theta. Okay, so let's take a look at that. Okay, so interesting. So the first thing I'm noticing when I look at this, so maybe we'll move this up. So the first thing I'm noticing is that this is equal to -1 times this. So maybe we could factor out a negative here, and then these will match and we can cancel. And you can convince yourself that's true, because if you redistribute, you will get this. So that factorization of -1 is fine. Okay, so those will cancel. And I have negative sine squared of theta over cosine squared of theta. Now, it might be tempting to call this tangent squared, but think about where you're trying to land, right? I want to land here. I don't want to land at anything involving tangents. So I think we're good with the denominator. We shouldn't do anything else with the denominator. Let's think about if there's a way to turn sine squared stuff into cosine squared stuff. And there is, right? So if we use the Pythagorean identity for sine squared, we know that that's equal to 1 minus cosine squared of theta. If I distribute the negative, I can write this as cosine squared of theta minus 1, right, if I distribute. And that's over cosine squared of theta. Okay, so yeah, that was a nice one. That was a nice one. So Pythagorean identity again to the rescue. Factorization to the rescue. Factoring out a -1 allowed me to cancel. Realizing that these were off by a factor of -1 was super nice. So I like that. And yeah, let's see what's up next. Okay, so yeah, let's work with the left side, see what happens here. So here I've got secant squared of theta times 1 minus cosine squared of theta. Let's distribute. Secant squared of theta minus secant squared of theta times cosine squared of theta. Well, I think we should realize something, right? Because secant and cosine are reciprocals of each other. And when you multiply reciprocals, you get 1. So this is equal to secant squared of theta minus 1. But that's a Pythagorean identity, right? That's one of our classic Pythagorean identities. And we know that secant squared of theta minus 1 is exactly tangent squared of theta. So that was pretty nice. Okay, let's take a look at the next. Could it be? This is the last one. We made it. Okay, cool. Quite a journey here, quite a marathon. Okay, let's work with the right side and show that it's equal to the left side. So 1 plus 2 tan squared of theta plus tangent to the fourth of theta. That's the same thing as, I'm going to write it in descending order of exponents. I don't have to, but I think maybe it'll be maybe a bit more obvious if I do. This should remind you of a trinomial that you can factor. It reminds me a lot of this. And in this case, you would say, oh, yeah, I can factor this into x squared plus 1 times x squared plus 1, or x squared plus 1 quantity squared. And we're going to apply that same thinking here because what's playing the role of x is exactly tangent of theta. So here we have the following. So this is tangent squared of theta plus 1 times tangent squared of theta plus 1. But actually, that's a Pythagorean identity, right? Tangent squared of theta plus 1 is exactly secant squared of theta. And in fact, I have it here as well. All right, so we did it. We made it through the Trig Identity Marathon. So folks, I hope that was helpful. And if you liked that video, give this a like, subscribe to the channel, share with your peers, your math buddies, and I hope to see you real soon. Take care. Bye-bye.